Okay, so let's start the lecture today. So, uh, okay, so I think last time we are trying to analyze the sum negative 2I summation m from 1 to infinity. Sorry, summation n from 1 to infinity n squared, a2 squared minus m squared a1 squared, okay, over 4 times n squared a2 squared plus m squared a1 squared. Okay. Yeah, so we are trying to show, like, we are trying to see if you can to apply the integral test, right? So basically, I'm thinking of like yeah, I think to apply the integral test, I need the error to be very small, right? Or okay, error to be very small. Okay. Yeah, so the integral, so there is no problem for the integral yeah, so there is no problem with n, right? So for n there is no problem. So we can, so when we sum over n, right? So we can bend it by yeah, so think of like this f of n, right? Okay, so we can bend it above by f of x comma n, right? Yeah, I mean like for each term it's better than that, not the sum. Yeah. So like yeah, maybe let's say x from 1 to infinity. Yeah, sum is bounded by that. Okay. And then, so the question becomes like, what happens if we, what happens for each n, right? So for, I know like for definitely for a fixed m, I can do like an estimate, because once I fix an m, I know that there is eventually it's decreasing, right? Let me think. Right. So if you're so if you move me along the y-axis, so what will happen? So for different values of n, right? So different values of n. So there might be some constant that's being added. No, not exactly, but there is still something added on the denominator, right? So yeah. So what would happen exactly? Okay, so I'm trying to apply the error test. So how can I control the error, right? Yeah, so how can I control the error? So if I have, let's see, so imagine that, so this is like the x, and then this is like the y, and then so your function is increasing in which way? So so can we actually, yeah. So here, okay. Let's take the second derivative of this function with respect to this variable m. Okay. Let's see where the function is eventually decreasing. And then maybe we can analyze from there. Okay. So f of xy is equal to x squared a2 squared minus y squared a1 squared over 4x squared a2 squared plus y squared a1 squared. Okay. Let's take a second derivative about this y here. So first derivative, so 16x squared a squared plus y squared a, sorry, x squared, 16x squared a2 squared plus y squared a1 squared squared, sorry, to the fourth power. So derivative, oh shoot, what I'm doing. So yeah, so partial f partial y of xy, and then the derivative at the top, which is negative 2y a1 squared times the same thing minus, okay, hold the same, and then derivative at the bottom, which is 64 times x squared a2 squared plus y squared a1 squared to the third power times the derivative inside, which is 2y a1 squared. Okay, so this is equal to what? Okay, so you can cancel out a copies of third power, right? Because these two numbers, I don't think they are equal to 0, because this x and y, they are not equal to 0, right? Because we start at point 1, 1, okay? So we are not at the point 0. So, and then this a1, a2, this a1, a2, they are not equal to 0, okay? So, yeah, so therefore you have 16 x squared a2 squared plus y squared a1 squared to that's the 1 power, okay. So here it becomes negative 32 y a1 squared times x squared a2 squared plus y squared a1 squared. Okay. So this term, it has 64. Wait. Okay, let's continue. So, 64, minus 64, shoot. So there is a 2y, so minus the 128 times y a1 squared, okay, and this times that, just the x squared a2 squared minus y squared a1 squared. Yeah. Okay. Yeah, so therefore, I think we can like simplify this guy, right? So let's cancel out the 16. So 16, so this becomes 2, right? So this becomes 8, right? And then so yeah, so this is equal to negative 10 y a1 squared, okay, and then times no, what I'm doing. Okay, what I'm doing here. So, yeah. So this is negative 2. So you pull out like yeah. So this is equal to x squared a2 squared plus y squared a1 squared minus 4. Okay, here we go. So minus 4 times this plus 4, okay, should be plus. Wait, you pull out the so plus 4 times x squared a2 squared minus 1 squared a1 squared. Is that right? Okay. Okay, that should be right. Okay. It's right, okay. So x squared a2 squared plus 1 squared a1 squared. Okay, so okay. So this should be so 5, right? So 5x squared a2 squared plus, sorry, minus 3, okay. y squared a1 squared, okay. And these are gone. Okay. So let's take another derivative. Wait, I don't think I need to take another derivative. So, what do I want to do? So, I want to see where the slope is changing, right? Yeah, I think I have to take another derivative. So I think on the bottom I have x squared a2 squared plus y squared a1 squared squared. Okay. So for the first derivative at the top, I get so first I think this is the product rule, right? So first I take the derivative at the top, at the left, keep y the same. Yeah, so let's switch it to this bracket here. Okay, so negative 2 a1 squared, and then the right the same, 5x squared a2 squared minus 3y squared a1 squared. Okay. And then plus, okay. Oh, sorry, minus. Okay. And then 2y times the derivative of the right part, the other part. So 2y a1 squared. Okay. What is the derivative inside? 6y. Negative 6y a1 squared. Okay. Okay. So yeah, so this one multiplied by the top, the bottom one. Okay. X squared a2 squared plus y squared a1 squared. Okay. And then then minus. So this is fraction. Okay. Yeah. Minus. Minus what? Minus. So the duty of the bottom, which is 2y a1 squared, right? Times the top part. The top part is just 2y a1 squared, right? Times the top part. 5x squared minus a2 squared minus 3y squared a1 squared. Okay. Okay, so let's see, what did we get? Okay. Okay, I don't need to care about the bottom part, right? So because the bottom part is now equal to 0, okay. So I only need to care about the top part. So for the top part, I got. Wait, what did I get? So what did I get for the top part? Okay, so here, okay, so here this is like 12 y squared a1 to the fourth power, right? Okay, and then you have a so here you get negative 10 x squared a1 squared a2 squared, right? Okay, and then plus 6 y squared a1 to the fourth power, right? Okay. So therefore you get so this is negative 10 x squared a1 squared a2 squared plus 18 y squared a1 to the fourth power. Okay, so times x squared a2 squared plus y squared a1 squared. Okay, so this guy is 4y squared a1 to the fourth power, right? Okay. So now you have this one plus I can write out 4y squared a1 to the first power 5x squared a2 squared minus 3y squared a1 squared. Okay. So it is equal to so negative 10 x to the fourth power a1 squared a2 to the fourth power plus 18 y to the fourth power a1 to the sixth power. Okay. Plus okay, so this is equal to what? This is equal to 20 x squared y squared a1 to the fourth power a2 squared. Okay. And then minus 12 y to the fourth power a1 squared a1 to the sixth power. Okay. Okay, so here it cancels and becomes 6, right? Okay. So I'm letting this guy equal to 0. Okay, because all the numbers are all positive, right? So yeah. Okay, so set them equal to 0 means that finally I get 10 x to the fourth power a1 squared a2 to the fourth power equal to 6y x squared y squared a1 to the fourth power. Okay, so I think it is so let's think about this one. So yeah. Okay, so let me copy down this polynomial here. Okay. Okay. Yeah, so I was thinking about problems whether it can be solved using because I think there is a theorem about uh, the errors for the Riemann sum, right? Yeah. So what is the error about Riemann sum? Yeah, let me check. Yeah, so for a I think the error, it has something to do with the wait. Yeah, with the derivative bound, right? Oh yeah. Oh. Okay, so if the derivative is bounded, then I think by the okay. So if the derivative is bounded, then the error can be at most. Wait. No. Yeah, so okay. I think you want to estimate the error, right? So what I want to do is that so what do I want to do? I want to compute the so what do I want to compute? Yeah, so yeah, so what yeah, I think I want to compute like yeah, the zeros of the Yeah, I don't think I need to compute second derivative. I think I only need to compute the first derivative. Because the second derivative means the change of concavity, right? I don't think I need concavity yet, because I think I only need I only need to care like where does the function start to decrease, right? Or increase, yeah. So I only need to care where the function start to either increase or decrease. I think eventually it would decrease, because when this y is getting more and more negative, right? So this is positive. Wait a second. So will this function still? Yeah, so it will be very, very negative, but it will be less negative. Okay, if you divide by m squared. I think it's increasing, right? So it is yeah, it will be increasing, because this term is positive. This y is positive and this is negative. Okay, so this negative sign cancel out with this negative sign. So yeah, so basically you just ignore that. This is also positive. Yeah. So wait. Oh, okay, I see, okay. Yeah, never mind, it has two terms, okay. So, yeah, so if you multiply these to the first term, then it could be negative, right? Because if you multiply this to the first term, but as this y getting bigger and bigger, so this second term actually would dominate the first term. So this is actually negative. A negative something times a negative something become positive, yeah. So the function is eventually is increasing. Okay. So yeah, so therefore I think we can just set the first derivative equal to 0. Okay. So let me just keep a record of the second derivative in case. I need it somewhere really. Okay. Yeah, let me just erase this part. Okay, so yeah, so let's solve this. Equal to 0. So y can be equal to 0, right? So this implies that. So we want to solve for 5x squared a2 squared, which is equal to 3y squared a1 squared. Okay, so you have 5 over 3 x squared a2 squared over a1 squared. Okay, I got a very nice number here. So yeah, so basically since y is always positive, right? So you just do square root of 5 over 3 times this x a2 over a1. Okay. So So this is a critical point. Okay. And yeah, so this is a critical point. So therefore, okay. So I think what really matters is just this guy, right? So I think after this guy, this function is is like increasing. So therefore, we know that. So what do we know? If we like because it's increasing, and then if we just mirror it around x-axis and do reflection, and then we know that. So this is actually a decreasing function, right? So a decreasing function, we are free to apply the integral test. Yeah, so for a decreasing function, so we know that the function has well estimate. Okay. Wait. I don't think. Yeah. So I think we are in the case of double integral, right? Yeah. So what will work for the double integral? Is there a Riemann sum estimate for the double integral? I'm just really curious. So multiple integration, double integral over rectangular region. Yeah, so I'm looking at the where is, okay. Okay, see. Okay, so basically, yeah, so if we can somehow show that this derivative is bounded, right, over this region, And then, since the derivative is bounded, therefore, we know that so since the derivative is bounded, so when we like integrate over this small region, right? Wait. So we can actually find a bounds. So starting from the left endpoint, right? So starting from the left, starting from the left endpoint, yes. And then, since we know that the derivative is bounded, so therefore at any point, right, it is equal to integrate from the left to the y value that corresponds to this point of the derivative of f over partial f partial y dy. Okay. And since partial f partial y is bounded, so therefore this value is less than equal to you integrate over the absolute value of the derivative. Yeah. So okay. And then you show that the difference between these 2 points, between any point and this left end point, is actually bounded by you integrate over the derivative of you integrate over the upper bound of the derivative over this interval, right? Okay. So, is there an upper bound for the derivative? I think there is an upper bound for the derivative because okay. Maybe I'm running out of time. Okay. Yeah, so I think maybe I should start next time. So, okay, so our goal is to try to find an upper bound for the derivative.